Hello, thank you for attending this talk. My name is Zhiding, and I'm a senior research scientist with NVIDIA. In this talk, I'm going to discuss the challenges in weakly and self-supervised learning and present some recent proxy label approaches that address these challenges. In machine learning, a fundamental problem we care about is generalization. If we think of data as the support of knowledge, it is not hard to see that the generalization ability of a learning system is largely determined by the training data. However, real-world data are not perfect. We may encounter domain gaps, data bias, unseen data noise, and many other challenges. These challenges may all potentially limit the generalization performance of a learning system. Ideally, one may improve the generalization by having an infinitely large training set. In reality, however, this is often infeasible. A clear reason is that labels, especially strong ones, are often much more costly to obtain. Even though data can be available in most cases, arbitrarily increasing the dataset is likely to result in challenges including inexact supervision, incomplete supervision, and inaccurate supervision. There are other challenges as well. For example, labels by nature can be versatile and take diverse forms. In certain cases, such as robot interaction, they can be sequential and sparse. With the challenges from both imperfect data and imperfect labels, future AI systems should have the ability to improve generalization by learning continuously on new data. This requires the system to leverage diverse forms of weak supervision, or even self-improve on completely unlabeled data. Achieving this goal is challenging. A clear issue is the uncertainty or ill-posed nature of the problem due to the lack of constraints. In other words, learning without enough supervision often leads to degenerated trivial solutions which are not desired. How to avoid these trivial solutions while effectively extracting meaningful information from data has been a central topic for this area. Fortunately, there is a set of common toolkits which can battle with the degenerated solutions. For example, self-supervision recently emerged as a powerful tool to learn meaningful representations by designing proxy tasks. In fact, the proxy label approaches, which we are going to mention throughout this talk, broadly belongs to this category. There are a variety of other useful methods as well. For example, we know that a visual scene is often highly structured. Taking this into account may significantly reduce trivial solutions by ruling out impossible configurations. One may also inject useful regularization and inductive biases to benefit the learning process. Another potential constraint is domain prior. In a street view, for example, sky is often above, whereas road is at the bottom. Finally, synthetic data provides a practical solution to obtain large quantities of labels at low cost. This is particularly important for robot and autonomous vehicle simulation, where labels can be very difficult to obtain outside the simulation. Many of these approaches will be leveraged by the works coming in subsequent talk. Now, I will move to the first part of the talk. In this part, I will give a brief review on proxy label approaches and demonstrate their applications on learning with unlabeled data. Semi-supervised learning considers the problem where only a portion of the data is labeled, and the task is to use the unlabeled data to obtain a better classifier. A typical way to address semi-supervised learning is to add a regularizer R, which serves as an unsupervised loss over the unlabeled data. There are many ways to define R. A recent approach called self-ensembling defines R as the consistency between the model predictions given perturbed inputs. The core idea being that a good semi-supervised model should produce consistent predictions on unlabeled data. In this way, the model prediction itself has become the proxy labels, even though the real ground truths of the unlabeled data are absent. self-ensembling achieved great success and became very popular on semi-supervised learning. Many latest state-of-the-art methods are more or less variants of such approach. Let's see how self-ensembling works intuitively. Assuming that there is a small set of labeled data. These labeled data can give an initial classifier. However, due to the limited number of labeled data, the classifier is likely to be imperfect by cutting through many high-density areas. Whenever the classifier cuts through a high-density area, the consistency term R is likely to give large penalties because data near the classifier produce inconsistent predictions. Finally, the classifier will be forced to cut through low-density areas in the feature space while complying with the initial labels. An example of self-ensembling is the pi model, where predictions are perturbed by data augmentation jointly with random dropout. Another example is the mean teacher model, where a teacher is created by taking the exponential moving average on the model parameters. Then, the model is learned by imposing consistency between the teacher and the noisy student. In addition to self-ensembling, recent state-of-the-art methods also sharpen the proxy labels or even replace them with hard pseudo-labels. Doing this essentially leads to regularization of the models with entropy minimization. This is because hard pseudo-labels encourage the model to output sharp predictions rather than soft ones. Pseudo-labeling is widely found useful with good performance. An intuitive explanation is that entropy minimization forces feature embeddings to be more concentrated in the feature space, therefore creating larger low-density areas that benefit the semi-supervised learning. Another important example of learning with unlabeled data is unsupervised domain adaptation. In unsupervised domain adaptation, one assumes that there is a labeled source domain and an unlabeled target domain. Given a model trained using the labeled source data, the task is to consider how the target domain generalization performance can be improved using the unlabeled target images. An important application of unsupervised domain adaptation is synthetic to real generalization, where the goal is to leverage unlabeled photorealistic images to improve the generalization ability of synthetically trained models. In the recent two works, we found that deep self-training surprisingly effective in unsupervised domain adaptation. It is worth mentioning that since then, deep self-training has become one of the predominant streams in unsupervised domain adaptation with state-of-the-art performance, along with other popular approaches such as GAN and adversarial training. In the first work, we propose a class-balanced self-training framework where we formulate a task as an EM-like problem by treating the target domain pseudo-labels y hat as latent variables. The pseudo-label of each sample is defined to be either within a probability simplex or a zero vector. A zero vector indicates the ignorance of self-training loss on this sample due to insufficient confidence. In addition, lambda k are the parameters that could rebalance the confidence of each class to prevent the diminish of small classes in self-training. Minimizing the loss with respect to the pseudo-label y hat leads to the solution based on two criteria. First, what is the argmax output of balanced softmax? And second, whether the confidence is above the class-specific threshold. Compared to vanilla self-training, we found that class-balanced self-training improves significantly with the introduction of confidence rebalancing. Solving the above self-training problem essentially leads to an alternative optimization algorithm between loss minimization with respect to pseudo-labels and model retraining given fixed pseudo-labels. Here, we show an example on GTA 5 to cityscapes. An initial source model is trained using source images and labels. The self-training framework then involves the iterative process of pseudo-label generation and network retraining. This process is repeated for several iterations. Finally, the retrained network will produce much better predictions in the target domain. An issue with self-training using hard pseudo-labels is having overconfident mistakes. such mistakes often come from two cases. First, imperfect source model due to its limitation on target generalization. And second, inherent label ambiguity on the target samples themselves. Since target domain labels are not available, the mistakes can accumulate and get magnified towards a degenerated solution over time. In the second work, we introduced two types of confidence regularization to address this issue. The idea being that we still want some level of entropy minimization in self-training, but do not to the extent of over-minimization through some regularizations. Here, we visualize some qualitative results on GTA-5 2 cityscapes. In the top two rows, we visualize the prediction results on two cityscapes validation images. One could see that CBST corrects a significant portion of mistakes made by the source model, whereas CRST further improves over CBST. In the bottom row, we visualize the independent frame-wise inference results of CRST compared to the source model. In addition, quantitative results in our paper also indicate consistent performance gain brought by both proposed methods, which led to state-of-the-art adaptation performance at the time of publication. Finally, it is worth mentioning that the proposed method helped us to secure both first place and third place in the domain adaptation track of the workshop on autonomous driving challenge at CVPR 18. Another application we recently looked into is Person Re-ID. Person Re-ID has wide applications in multi-camera tracking and AICT. Like face recognition, the problem is not a closed set classification problem where training set and test set share the same label space. Instead, the test set contains new IDs that are not seen during training, and problem cares about the verification between pairwise images by measuring their distance. As a result, both face recognition and Person Re-ID can be viewed as open set metric learning problems. A predominant stream of the literature train deep neural networks on the training set and use them as feature extractors to output the distances between images during testing. In CVPR 19, we proposed DigiNet, a Person Re-ID framework which disentangles an image into an appearance space and a structure space. In the paper, we showed that by swapping the code, we can compose unseen new images in a combinatorial pairwise manner. We also demonstrate how the composed new images are able to help the task. However, even though DigiNet was able to achieve state-of-the-art performance within the same domain, additional studies indicate that cross-domain generalization performance can drop significantly with the domain gaps. For example, the MAP performance on Market 1501 test set dropped from 86 to 26.8 if we simply change the training set to Duke. In light of this issue, we followed up DigiNet by studying the problem of cross-domain Person Re-ID. Actually, this work is just accepted as an oral presentation in this ECCV, and you are welcome to attend our paper session and ask questions. Since Person Re-ID is an open set problem, cross-domain Person Re-ID also becomes an open set domain adaptation problem. As a result, the proxy label approaches previously introduced cannot be directly applied here due to mismatched label space, and this further adds challenges. The way we tackle this problem is to disentangle the representation from both domains into a shared appearance space and domain-specific structure spaces. We believe that the shared space gives a better starting point by being more domain invariant, and we perform open set adaptation only within this space. Specifically, we propose a cycle consistency framework to disentangle the domain invariant shared representation and leveraging it as a self-supervision to reduce domain gap. We also add adversarial losses to further enforce global distribution matching. Finally, given the disentangled representation space, we use dbScan as a clustering-based proxy label approach to generate pseudo-labels across the label space. The clustering and pseudo-label generation, together with disentangling, forms an iterative open set self-training loop. We tested DGNet++ comprehensively on multiple cross-domain settings and showed performance gain over several recent competitive methods. With ablation studies, we validated the effectiveness of each proposed component. We also showed that removing any one of the components leads to significant degeneration, indicating that our design is necessary beyond naive combination. Finally, we showed that DGNet++ significantly increases the cross-domain performance over DGNet. Besides quantitative evaluation, we also visualize our cross-domain image compose results and compare several related works. Our method is the only one which can simultaneously succeed in swapping the code while giving high-quality generation under the challenging cross-domain scenario. This shows that DGNet++ is indeed learning meaningful disentangled representation with correct attention. In the first part of the talk, I briefly reviewed proxy label approaches and introduced several works that focus on learning with unlabeled data. In the second part of the talk, I'm going to extend proxy label approaches to even more complicated scenarios with various levels of supervision. Specifically, we are interested in the problem of weakly supervised object detection. Traditional object detection and instance segmentation often require bounding boxes containing detailed localization. Instead, weakly supervised object detection aims to learn a detector by only using image-level labels that indicate the classes of present objects. To address this problem, one may consider the set of object proposals given by any off-the-shelf proposal generation method within each image, and treat them as bags. This exactly turns the weakly supervised object detection into a multiple instance learning problem where positive bags indicate that at least one of its samples is positive, whereas a negative bag indicates that all samples of the bag are known to be negative. The difficulty of the problem lies in the fact that one doesn't know which samples are positive. It is a latent variable that needs to be jointly optimized and figured out by the algorithm itself. To this end, Bailan et al. Proposed the weakly supervised deep detection network, which is a well-known framework to address the problem. Specifically, their work disentangles the ROI scores into two branches and use different normalization as an inductive bias to encourage the encoding of classification and localization information respectively. The framework then combines these two branches and uses sum pooling as a reduction over the set of all proposals before going to image-level class supervision. Even though the method achieves good performance, it still faces many challenges such as missing instance, grouped instance, and part domination due to the lack of constraints. In light of the challenging nature of this area, we came up with two works in this year's CVPR and ECCV that try to address the challenges. In the first work, we addressed the classical weakly supervised object detection problem and proposed a new framework that leads to state-of-the-art performance on this task. In the second work, we further considered the problem of omni-supervised object detection, which is a generalization of both weakly and semi-supervised learning with a spectrum of supervisions at various levels. Before introducing our framework, another related work is online instance classifier refinement. In this work, weakly supervised deep detection network is used as an image branch to produce an initial estimate of ROI scores using image-level labels. The ROI scores are then turned into proposal-level pseudo-labels by selecting the most confident proposal and other highly overlapped ones as positive and setting everything else as negative. The pseudo-labels are fed into several repetitive refinement branches and supervise them in a per ROI supervised manner. In some sense, online instance classifier refinement can be viewed as another example of teacher-student model with self-training in a weakly supervised setting. The method is simple but very effective and led to considerable improvement over weakly supervised deep detection network. However, Upon thinking more carefully, the fact that choosing only one positive instance in online instance classifier refinement may not always be reasonable. Even though empirically working well, it contradicts with the fact that there could be multiple instances in the same image. This exactly motivated us to propose this multiple instance self-training framework, where we allow multiple positive instances by considering the pool of top-ranked proposals within a certain portion. However, our framework goes beyond just allowing multiple instances with several additional features. We notice that unlike dense prediction such as segmentation, object detection is special by having an NMS stage which may correspond multiple proposals to a single instance. Considering this aspect, our framework is instance associative by considering instance-level pseudo-boxes instead of ROI-level pseudo-proposals in many previous methods. And because of this, we are able to treat the pseudo-labels as a full box supervision and perform self-training with ROI regression. Finally, we incorporate IOU regularization to promote spatial diversity of the pseudo-boxes. Another major technical contribution is that we adopt a data-driven, end-to-end learnable drop log regularization to avoid degeneration of self-training to object parts. Specifically, we reparameterize the sampling process in traditional drop log with a small network and gumball softmax. We turn this module concrete drop log and formulate its learning problem as a minimax game where the parameters are learned to maximize the network loss. This encourages the concrete drop log to focus on dropping the most discriminative parts in a data-driven manner. We conduct comprehensive ablation studies on Pascal VOC. The results show that all components, including multiple instance self-training, ROI regression, and concrete drop log, all gave significant performance gain. We also conducted comprehensive experiments on MS COCO and outperformed previous competitive methods. Our method is the current state-of-the-art on all the above three datasets. And it is worth mentioning that we only report single model performance, which outperforms previous methods with model ensemble. Here are some qualitative results with the proposed method compared to online instance classifier refinement. One could see that the proposed method comprehensively improves the result in terms of the three challenging issues mentioned earlier. Here are some additional visualizations and failure cases on the right. We notice that the weakly supervised object detection problem is still very challenging, and our method inevitably makes mistakes that are typical in this area. Okay, now let's think beyond weakly supervised learning and consider the situation where we have a full spectrum of supervisions at different levels. We want to consider the most general case with minimum assumption on the mixture of supervision. For example, it could be 100% tag, which leads to a classical weakly supervised object detection, or 100% boxes, which turns into fully supervised detection, or any other arbitrary mixture portion. In addition, part of the data, even though not all of them, may also be unlabeled. In this case, can we come up with a single unified framework that can handle them all? At a first glance, one may think that the problem isn't that hard with multitasking. Let's say for the mixture of tags and boxes, what about having different learning heads for them separately? The answer is not that simple. A problem for doing this is the conflict of which head to trust during inference. Looking at the design of different heads more carefully, we notice that the similarity between refinement branch in weakly supervised head and the fully supervised one. As a result, we can adopt a single unified head design that can handle both supervisions. Let us further extend to more generalized scenarios with points and scribbles and see how the proposed unified head works. Turns out that the problem isn't that different from learning with tags, except that the points and scribbles can provide additional localization information that can help to refine the proposal candidates. When we have images with bounding boxes, one naive solution is to directly supervise the student branch. This, however, did not leverage the fact that boxes can also be used to train teachers. If teachers are not sufficiently trained, they could be weak and poison the representation when learning with partial supervisions. As a result, we propose to better couple teachers with strong supervisions, making them strong by using box ground truths to directly supervise the latent variables in the teacher module. This will guarantee that no matter supervision is full or partial, the teacher branch always gets trained. Finally, when there is unlabeled data, we can generate pseudo tags by taking confident classes from teacher's prediction. Then everything else follows the setting of learning with tags. In order to simulate points and scribbles on MS Coco, we use distance transform and skeletons to sample points and scribbles. We conduct comprehensive experiments with different partitions of MS Coco and different backbones. Experiments indicate that the proposed framework can handle all different situations of the input annotation, ranging from full box to full tag, point, scribble, as well as omni-supervised setting with a mixture of them. In omni-supervised setting, we show that both the unlabeled data and extra supervision help to improve the performance. We also conduct ablation studies showing that both strong teacher and the localization information from points and scribbles improve our results. Here are visualizations of the predictions when trained with different supervisions. One could see that there is a consistent tendency of better localization with less false positives and part domination, with the supervisions being stronger. We consider a budget-aware omni-supervised detection setting by considering different annotation policies that have the same amount of estimated budget. Interestingly, we found that the policy with a combination of boxes, points, and unlabeled images works slightly better than pure boxes and unlabeled images. This shows the possibility of finding more cost-effective annotation policies than having pure boxes, which is commonly considered. We intend to unify both works and release them under Witectron, a platform for learning object detection with weak and partial supervisions. Stay tuned for our updates. Lastly, I want to give some conclusions and look into the future. In terms of conclusions, we've shown that eliminating the uncertainty is really the key in weakly and self-supervised learning. There are certainly many other potential issues we didn't cover in this talk, but I would say that the majority portion of the efforts in solving these problems can be considered as battling with uncertainty. I also want to say that it is important to let multiple methods and multiple levels of supervision mutually constrain or help each other, even though this means making things more complicated. I imagine that it will be difficult for any single method to solve all the problems alone, as each of them may have its own weakness and strength. In this talk, we have several examples showing the benefit of having things together than single items alone. In terms of future works, I think it will be important to consider more complicated, human-like platforms that support multimodality, multitasking, and post-deployment continuous learning with human interactions. I think human is always the best example where we can get inspiration from towards the path of artificial general intelligence. Thank you for attending this talk.